Hi viewers, welcome to the second lecture of the online series of lectures on Introduction to Category Theory. Last lecture, we discussed very generally what category theory wants to achieve in a general mathematical setup. We encountered the definition of a category and a functor in the process. We also studied some important examples of categories during the first lecture, one of which were vect C, the category of all vector spaces over the field of complex numbers. In mathematics, category theory is learned in a very abstract fashion. In order to make it a more down-to-earth style, in this second lecture, we will start developing all the tools of category theory in the framework of a specific category called the category of sets, which will be denoted by set. Okay. So set is a category where the objects are simply sets and the morphisms there in this category are functions between sets. So we will try to understand these constituent objects and the morphisms of this particular category set in this lecture. Let me define sets first. By sets I mean the objects of this category set. So we are discussing sets and functions. Set. A set X is a collection of things X in X. We read it as X in X, small x in the big X, each of these things, each of which is recognizable as being in X. It means that if you are given a thing, you will be able to identify if it is in the given set X or not. And each pair X prime in big X, one can determine if X is equal to X prime or not. Alright? So this is the definition of sets, the objects of this category set. Now let me write down a few important notions related to sets along with the annotations. The first being the null set. This symbol denotes the set with no elements in it. This is also called the empty set. The second one being this symbol denoting the set of natural numbers. The set of natural numbers. The third one being the set of integers. And so on. The set of integers. This is the set of integers. Okay. Now we need to introduce the notion of subsets. Given two sets A and B, when one of them will be a subset of the other. Let me write it down. If A and B are sets, we say that A is a subset of B, and we write it as this if every element of A is also an element of B. Is also an element of B. Okay? So using this notion of subset, we can immediately see that the set of natural numbers is indeed a subset of the set of integers. Okay, so now we come to the notion of set. We come to the notion of set builder notation. It is another notation to denote certain sets, which is called set builder notation. Okay, so now let us try to denote the set of even integers. How can we denote it? The set of even integers can be written as this. This means such that n belonging to the set of integers such that n is even. Let us take another example. So this is the example of the set of even integers. Let me give you another example where we can use set builder notation to denote the set. The set of integers which are greater than 2, How can we denote this set using set builder notation? We can denote it as n being in the set of integers such that n is greater than 2. So this set is denoted by the set builder notation. Also, there is an equivalent way of denoting the same set. We can write it as n belonging to the set of natural numbers such that n is greater than 2, or n belonging to the set of natural numbers such that n is greater than or equal to 3. It is easy for you, it is pretty obvious for you to understand that all these notations denote the same set. So there are certain ways of picturing sets. So the most straightforward way of drawing a set is by a bag full of dots. So this is a bag labeled by X, which is the underlying set, and this bag contains 9 dots. 5, 6, 7, 8, 9. So this represents the set X with 9 elements in it. Okay. So if I have an empty bag Y, it represents a set Y with no elements. In other words, Y is an empty set. Okay. Now, some more notations related to set theory. More notations. So, there is a symbol. There exists. We read it as there exists So we have already dealt with the example of the set of even integers. We can write the set of even integers also in the following way. N belonging to the set of integers such that there exists M in the set of integers such that, I abbreviate such that with S dot T, 2M is equal to N. So this notation also designates the set of even integers. Okay. So let's take the example of minus 8. Minus 8 belongs to this set, and for this minus 8, M is equal to minus 4, which is also in the set of integers. Okay? So far so good. We have another symbol which is also frequently used in set theory. This means there exists a unique For example, the statement there exists a unique real number x such that x squared is equal to 0 means that there is one and only one real number whose square is 0. This is indeed true, since we know that that particular real number is simply 0. Okay. On the other hand, what if I write there exists a unique real number such that x squared is equal to 4? Is it true? Give it a thought and realize that it is not true. Why? Because for both 2 and minus 2, x squared will be 4. So that there is no unique x for which x squared is 4. But we could modify this statement, which will be true, in the following way. There exists a real number such that its square is 4. This is indeed true, if you drop that uniqueness sign. Okay? Good. I give you another example related to these notations of basic set theory. Suppose we want to denote the set of natural numbers Okay, so the statement that the set of natural numbers is not bounded above is not bounded, meaning that whenever you mention a natural number, there is always a natural number which is bigger than the given natural number. Or that for each natural number, there is a larger natural number. So this statement can be expressed mathematically as for all. This stands for all. For all m in the set of natural numbers, there exists another natural number such that n is greater than n. This statement implies that the set of natural numbers is not bounded above. Okay, now it's time for an exercise, which is a pretty simple one. One can do it immediately, which asks you to find all possible subsets of this set 1, 2, 3. Okay? Find all subsets of A. This is the first exercise. So this is pretty simple. I don't bother you with a very easy exercise. So there are 8 possible subsets. You can immediately see that the single element subsets are 1, 2, 3. There are 3 possible 2 element subsets. 1, 2, 2, 3, 3, 1. By the way, note that 3, 1, this set is the same as the set 1, 3. Okay? Ordering does not matter in denoting the elements of the set. Okay. And there is only one 3-element subset of A, which is A itself. And of course, there is the null set, which is also a subset of A, previously. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 possible subsets of A. Okay. Now there is this notion of power set associated to a given set. So let me write down the definition of a power set. The collection of all possible subsets of a given set S is again a set. Is again a set which is a set of subsets of a given set, of course. Called the power set, called the power set of the given set. Given set S, denoted by curly P of S. So in the previous example, the power set of the 3-element set A is the following set. So there are 8 elements in this power set. 1, 2, 3, 4, 5, 6, 7, and 8. Okay? Those elements are also sets, which are precisely subsets of A, the given set A. So, important thing is to note that the way we write this set thing, with the curly braces, these is not the notation for a set. It denotes an ordered pair, so one has to be precise with these notations. There are students which make mistakes in writing precisely denoting sets. Sometimes they denote sets with this bracket, with this simple bracket. It does not make sense. They have to denote sets with curly braces. Okay? So far, so good. Now, I move to the discussion on the morphisms of the category set, okay, which are precisely functions between sets, as discussed earlier. So the morphisms of this category set are precisely functions between the objects of set, which are sets. Okay. The morphisms of set are precisely function between sets which are objects of set. Okay? So now let me give you the formal definition of function. Okay, if x and y are two given sets, then a function from x to y denoted by is a mapping that sends each element x in x to a unique is important, unique element of y. So that unique element in y is denoted by fx in big Y. We call x, if x, the domain of the function f, the domain of the function f and y, the codomain of f. Let me draw a picture first to illustrate what it precisely means by that underlined word unique. Let us denote the domain of the given function with x and the codomain of the given function with the given function of the given function y with y. So there are 4 elements in the domain. It is also important to have that in each. x1, x2, x3, x4. These are the 4 elements of x. I have 5 elements in y, y1, y2, y3, y4, and y5. Let us make the assignment as follows. x1 is mapped to y1. x4 is also mapped to y1. There is no harm in that. x2 is mapped to y2. And x3 is mapped to y4. Okay? Alright. So, first of all, note that in this process, each element of x is mapped to some element of y. Okay? So there is always an arrow emanating from each of the elements of x. Okay? So one arrow is emanated from x1, another arrow is emanated from x2, also an arrow is emanated from x3, another arrow is emanated from x4. So there is no element here from which there is no arrow which is not emanated. So always an arrow is emanated from each element of x. Okay, so another fact here is the uniqueness thing, which tells you that not more than one arrow can be emanated from a single element of x. Okay, which is not happening here, as we can see. That not more than one arrow is emanated from x1. The same holds for the rest of the 3 elements. Okay, which means that each element x of big X is mapped to a unique element of y. Okay, so let me write this fact here. Note that for every element small x in big X, there is exactly one arrow emanating from X but there is no harm for an element y for an element y, small y in big Y, there can be several arrows, pointing to y. Which is happening here. Since there are two arrows, as we can see from the picture, that there are two arrows which are pointing to y1. Also, it can be the case that there are elements in y for which there are no elements of x which are assigned. Okay? Meaning that there can be no arrows at all pointing to elements of y, such as y3 and y5. For y3 and y5, there are no arrows which are pointing to them. Okay. Now, this was the general definition of a function. So let me end this segment by giving you another definition, a very quick definition of image given a function f from x to y, the elements of y that have at least one arrow pointing to them are said to be in the image of f. Formally, we denote the image of f with IMF, which is defined as the set of elements in the codomain such that there exists an element in the domain with fx is equal to y. So, here is another worked out example. I have written down here as exercise. Also in the lecture notes, it should be something like a worked out example. If f is the function as given in the previous figure that I drew on the board, I have erased it here. So, if you go back to the figure and see what the image of f is, you will immediately find that the image of that function is precisely this three-element set. Okay? So this finishes the first segment of the second lecture. So I'll get back to you with the remaining part of the functions